In the realm of quantum teleportation, a novel protocol for bidirectional quantum teleportation, BQT, is introduced, leveraging the multipartite Glauber coherent state as a quantum resource. This state comprises the Greenberger-Horne-Zeilinger, ground, and Werner states, which are entangled and shared between two distant partners, Alice and Bob. By exploring the pairwise entanglement in symmetric and antisymmetric multipartite coherent states, the optimization of teleportation efficiency is achieved by adjusting the overlap and number of probes, constructing different types of quantum channels. To assess the roles of Alice's and Bob's trigger phases, two quantum statistical speeds are employed: quantum Fisher information, QFI, and Hilbert-Schmidt speed, HSS. The lower bound of the statistical estimation error, quantified by QFI and HSS, corresponds to the highest fidelity in both directions, from Alice to Bob and from Bob to Alice. The choice of pre-shared quantum channel is critical in achieving high BQT efficiency. The proposed scheme's implementation on current experimental tools is discussed, enabling Alice to transfer her even coherent state to Bob, while Bob transfers his odd coherent state to Alice. This research advances quantum communication networks, with significant implications for secure communications, quantum computing, quantum dense coding, and quantum key distribution. In the realm of quantum teleportation, researchers have extended the standard protocol to encompass various entangled quantum states, with a notable development being bidirectional quantum teleportation, BQT. This concept enables two users, Alice and Bob, to simultaneously transmit their quantum states to each other using pre-shared entanglement. This paper proposes a novel BQT scheme utilizing two independent quantum random trigger qubits, one corresponding to an even coherent state and the other to an odd coherent state. By combining the global state of the system and an entangled state between the even and odd states, a circuit is implemented in the Qiskit quantum computer, providing a measurement of the probabilities. To overcome the traditional fidelity barrier, the amount of shared state entanglement, quantified by Wooter's concurrence, the teleportation fidelity, and the success probability are derived. The trigger states and initial states of the transported qubits affect the fidelity and quantum Fisher information, QFI, of bidirectional teleportation, where both the maximum QFI and fidelity values are the same even when predicted at distinct polarization angles. The Hilbert-Schmidt speed, HSS, was determined using QFI, demonstrating how well this statistical speed quantifier can be applied to the BQT protocol. Furthermore, by optimizing the entanglement resources, high-fidelity teleportation can be achieved even in the presence of noise and decoherence. The even and odd coherent states form the basis of this protocol, enabling the transmission of qubit states bidirectionally using a single entangled state and two separate trigger qubits. The entanglement resources are carefully chosen to ensure that the teleported states are faithfully reproduced at the receiving end. Simulations using Qiskit are conducted to test the proposed BQT protocol in a controlled environment and its capacity to transfer information bidirectionally. By testing the protocol in a simulated environment, potential issues can be identified and the protocol can be optimized accordingly. Once the simulations are successful, the protocol can be implemented on a real quantum computer. In the realm of quantum technologies, multipartite coherent states play a pivotal role in achieving quantum supremacy, particularly within the BQT protocol. These states are characterized by their superposition between even and odd coherent states, which is essential for understanding the system's behavior. The overlap between these states is a key concept that highlights the transitions from GHZ-like states to Werner-type states and vice versa as p approaches 0 and 1, respectively. Furthermore, the paper introduces a bipartite splitting of multipartite coherent states, demonstrating how the system can be divided into two subsystems for further analysis. This section provides an in-depth exploration of the properties and importance of multipartite coherent states in quantum technologies, shedding light on their potential to revolutionize quantum computing and communication. In the context of bipartite quantum states, representation in the computational basis is crucial. Coherent states, characterized by non-orthogonality, necessitate an orthonormal basis for the Fock-Hilbert space. This is particularly important when encrypting logical qubits using even and odd coherent states. The encryption process leads to the derivation of the superposition of multipartite coherent states, a fundamental concept in quantum information processing. A key aspect of this derivation is the representation of the reduced density matrix ρ12 in the orthonormal basis. This matrix is instrumental in understanding the entanglement properties of the bipartite quantum state. Specifically, the concurrence of ρ12, a measure of entanglement, provides valuable insights into the quantum correlations between the two subsystems. The mathematical derivations and transformations of quantum states, including the bipartite case, rely heavily on the choice of basis. The orthonormal basis, in particular, plays a critical role in ensuring the accuracy and consistency of these derivations. Furthermore, the encryption of logical qubits using coherent states has significant implications for quantum error correction and quantum computing applications. The reduced density matrix ρ12 serves as a powerful tool for characterizing the entanglement properties of bipartite quantum states. By analyzing the concurrence of this matrix, researchers can gain a deeper understanding of the intricate relationships between quantum subsystems. Analyzing entanglement between two parts of multipartite coherent states is crucial for the proposed BQT protocol. The authors employ Wooda's formula to express the concurrence entanglement, resulting in equation 18, where C, ρ12, is the concurrence entanglement in the state. 16, and C plus or minus are functions of the overlap P and the number of probes n, as defined in equation 19. The concurrence entanglement is plotted as a function of the overlap P for different values of n in Fig. 1, demonstrating distinct behaviors for symmetric and antisymmetric multipartite coherent states. For symmetric states, the collective entanglement initially increases but eventually decreases to 0 as P approaches 1, where the resource states become separable. In contrast, the concurrence entanglement increases with increasing P and reaches its maximum value in the limiting case P right pointing arrow 1 for antisymmetric states. The authors identify the probe numbers n and the overlap P as controllable factors for achieving pre-shared entanglement in the BQT protocol. They then describe the proposed protocol, which employs even and odd coherent states for bidirectional teleportation between Alice and Bob. The protocol utilizes a multipartite coherent state as a quantum channel, involving 10 qubits. The even and odd coherent states are represented in the block sphere, as shown in equation 20, where ρ, e, even and ρ, o, odd are the density matrices of the even and odd coherent states, respectively. These states are expected to play a crucial role in interferometric detection of gravitational waves. The author's analysis highlights the significance of entanglement control in the BQT protocol, demonstrating the potential for precise manipulation of multipartite coherent states in quantum information processing applications. In the binary quantum teleportation scheme, Alice and Bob utilize multipartite coherent states, psi, to communicate their states, even and odd, simultaneously. Decoherence occurs at the end of the protocol, resulting in both sender and receiver obtaining a state with some decoherence. The size of the coherent components eta plays a crucial role in verifying quantum information technology. Each user possesses two distinct types of qubits: trigger qubits and storage qubits. Trigger qubits, initially specified as te and 2, are represented in the block vector expansion as ρ-te and ρ-2, respectively. These qubits facilitate the exchange of even and odd states between Alice and Bob. Storage qubits, comprising S1e, S2e, S10, and S20, are used to store and exchange quantum information. The implementation of binary quantum teleportation using Qiskit involves the application of X-gates, controlled NOT gates, controlled NOT gates, Hadamard gates, controlled Z gates, and phase shift gates to generate an entangled state. To perform the binary quantum teleportation protocol, Alice and Bob initially share a state of the form She S equals te S1e, S2e, even 2, S10, S20, odd circled times psi, following the Kiktinko steps reported in 35. The protocol begins by setting the user's quantum state as She S, a crucial step in the binary quantum teleportation process. The proposed BQT scheme for bidirectional quantum teleportation of coherent states begins with the initialization of the quantum channel, where two entangled qubits are shared between the sender and receiver. The sender applies a Hadamard gate to the first and final qubits of the trigger qubits, even and odd, followed by two controlled NOT, CNOT, gates to these qubits and the entangled state, psi. This prepares the trigger qubits in an entangled superposition state. In step 4, both parties perform two controlled NOT, CCNOT, gates on the trigger qubits, entangled qubit, and storage qubits, further entangling the system. Following this, the sender and receiver apply two Hadamard gates and two controlled Z gates to their respective trigger qubits, preparing them for the actual teleportation of information. The actual teleportation phase is described in step 5, where the sender and receiver use a phase shift gate CP on the entire system, followed by another controlled Z gate on the trigger qubits and entangled qubit. This phase completes the teleportation process. Finally, in step 6, the sender and receiver apply Pauli gates to their trigger qubits based on measurement outcomes, completing the BQT protocol. The fidelity of the quantum teleportation, a measure of how closely the teleported state matches the original state, is crucial for evaluating the efficiency of the BQT scheme. Factors such as entanglement, channel quality, and measurement efficiency influence the fidelity. The fidelity for the teleportation between the two users, FA right pointing arrow B and FB right pointing arrow A, is calculated using the density operators of the teleported and original states. The fidelity of quantum teleportation from Alice to Bob and from Bob to Alice is examined, focusing on the overlap parameter p, the number of partitions n, and the parameter m. Detailed expressions for fidelity are presented using equations 22 and 12. The choice of the pre-shared entanglement state significantly affects teleportation efficiency. For symmetric states, a separable state achieves maximum fidelity, while antisymmetric states require a maximally entangled state. Increasing the number of partitions n generally improves fidelity, with the best results at n equals 25. Optimizing these parameters is crucial for high-fidelity quantum teleportation. In this section, the authors utilize quantum Fisher information, QFI, and Hilbert-Schmidt speed to assess the credibility of the quantum teleportation protocol. QFI is a measure of quantum information transmission, providing the sensitivity of the quantum state to changes in the encoded parameter. The authors derive an analytical expression for QFI using the symmetric logarithmic derivative operator associated with the parameter xi. This expression involves the eigenvalues and eigenvectors of the density operator prescription, reformulated as a sum of two terms, one involving the variation of eigenvalues and another related to the variation of eigenvectors. For single qubit states, a simple and explicit formula for QFI is used, depending on the real block vector of the state. Additionally, the authors explore the Hilbert-Schmidt speed, derived from a family of distance measures between probability distributions, quantifying the sensitivity of distributions to changes in the parameter xi. By expanding the probability distribution p, xi, to first order and xi, the authors evaluate the distance between p, xi0, and p, xi0 plus xi, obtaining the classical statistical speed as a sum over the absolute values of the derivatives of probabilities at xi0, raised to the power of alpha and summed over all possible outcomes x. In quantum metrology, the Hilbert-Schmidt speed, a specific instance of quantum statistical speed, plays a vital role in quantum phase estimation and detecting non-Markovianity in open quantum systems. This speed is defined using the Hellinger distance, which measures the quantum distance between two states. Specifically, when the exponent alpha equals 2, the Hilbert-Schmidt speed is obtained. The significance of the Hilbert-Schmidt speed lies in its connection to the quantum Fisher information, a central concept in quantum metrology. The quantum Fisher information quantifies the maximum precision achievable in estimating a parameter of a quantum state. In the context of quantum teleportation, the paper derives analytical expressions for the quantum Fisher information and the Hilbert-Schmidt speed of teleported states. These expressions involve complex mathematical derivations, including the use of operator algebra and functional analysis. The derived expressions are crucial for understanding the quantum information transfer between two parties, Alice and Bob. By quantifying the precision of quantum state estimation, the Hilbert-Schmidt speed and quantum Fisher information provide valuable insights into the fundamental limits of quantum communication. Furthermore, these concepts enable the detection of non-Markovianity in open quantum systems, a phenomenon characterized by memory effects in the system's dynamics. The analytical expressions presented in this section form the basis for further exploration of quantum information processing and its applications in quantum communication and metrology. The page presents 4 equations crucial for the analysis of the proposed system. Equation FA right pointing arrow B1 defines the functional form in terms of cos, the, upsilon, n, m, p, and other variables, involving a complex combination of trigonometric functions, polynomials, and algebraic expressions. Equation FA right pointing arrow B2 represents the functional form of FA right pointing arrow B2, a function of p, n, m, the, and tho, also involving intricate trigonometric and algebraic expressions. In the FB right pointing arrow A direction, equation FB right pointing arrow A1 defines the functional form in terms of p, n, m, the, tho, and various auxiliary functions, such as xi, micro, epsilon, and kappa, exhibiting a complex interplay of trigonometric functions, polynomials, and algebraic expressions. Lastly, equation FB right pointing arrow A2 represents the functional form of FB right pointing arrow A2, a function of p, n, m, the, tho, and auxiliary functions increment, sigma, and tau, involving a complex combination of trigonometric functions, polynomials, and algebraic expressions. The auxiliary functions are defined in terms of p, n, m, the, and tho, involving intricate algebraic and trigonometric expressions, which are essential in the analysis of the proposed system. The study examines quantum Fisher information, QFI, and Halevo-Schumacher-Westmoreland, HSS, for a bipartite quantum teleportation protocol using multipartite Glauber coherent states as the quantum channel. Both QFI and HSS exhibit oscillatory features, with minimum and maximum values coinciding perfectly. This indicates that HSS can be used to pinpoint the precise moments when the estimated trigger qubit phases reach their best estimates, improving the efficiency of the bipartite quantum teleportation protocol in both directions. The top row of Fig. 5 demonstrates the behavior of QFI as a function of the trigger qubit's phases, under the same parameters as in Fig. 4. The QFI of the teleported states strongly depends on the number of probes n, the parameter m, and the overlapping p between the coherent states, specifying the pre-shared quantum channel. In the direction from Alice to Bob, the QFI of the teleported even coherent state increases with decreasing overlapping parameter pages. Comparing this behavior with the results displayed in Fig. 4, it is concluded that the maximum fidelity corresponds to the minimum variance of the estimated parameter nu-e. Perfect fidelity corresponds to 0 QFI, where the variance of Alice's trigger phase is diverged. In the second direction, corresponding to Bob towards Alice, and for fixed parameters n and m, the QFI and the teleportation fidelity increase with the decrease of the overlapping p. This indicates that the teleportation efficiency reaches its top values when the estimation of Bob's trigger phase diverges. The behavior of QFI is similar in both directions, but as QFI from Alice to Bob increases, QFI from Bob to Alice decreases. The bottom row of Fig. 5 compares quantitatively the QFI and HSS associated with the parameters of the trigger phases under the same conditions, showing that the minimum and maximum values of the HSS and QFI coincide perfectly and both exhibit oscillatory features. These results provide a qualitative indication that HSS can be employed to pinpoint the precise moments when the estimated trigger qubit phases reach their best estimates. HSS therefore performs the same role as QFI in improving the efficiency of the bipartite quantum teleportation protocol in both directions. The utilization of multipartite Glauber coherent states as the quantum channel brings forth numerous advantages that surpass those associated with other types of entangled states. The proposed BQT protocol is benchmarked against 7 other BQT and SQT protocols in Table I, highlighting its distinct features and advantages. By leveraging multipartite coherent states as a quantum resource, the protocol achieves efficient resource utilization, rendering it suitable for practical applications in quantum communication. Unlike previous approaches, the proposed protocol attains maximum fidelity by optimizing key parameters, including m for symmetric and antisymmetric states, n for the number of partitions, and p for overlap. This underscores the importance of utilizing maximally entangled resource states to achieve maximum BQT efficiency, which is realized through parameter optimization in our protocol. Experimental implementation of the proposed BQT protocol is crucial to validate its effectiveness. Notably, the protocol can be tested on various quantum computing platforms, including Quark, Qiskit IBM-Q, Quantum Inspire by Q-Tech, Rachid Forest, Quantum Programming Studio, and D-Wave. To ensure objectivity and credibility, the protocol is tested on Qiskit. Operating on a probabilistic basis, similar to quantum teleportation, the protocol requires both parties to possess trigger qubits and share an entangled state and a classical communication channel. The parties apply specific gates to their trigger qubits to create desired states in advance, followed by entanglement measurement, classical communication, and correction operations to transfer the quantum states. The protocol's details are elaborated in the following sections. The BQT protocol is demonstrated using a quantum circuit with 10 qubits, consisting of sender and receiver qubits. The circuit begins by preparing trigger qubits in unknown states using X gates, followed by the creation of 2 entangled pairs using CNOT and Hadamard gates. This setup enables the transmission of quantum information between the sender and receiver through entangled states. The circuit then applies a CCNOT gate on each pair of trigger qubits and their corresponding entangled pairs, collapsing their state into one of 4 possible outcomes. Hadamard gates are applied to qubits, odd and psi, followed by controlled Z gates between qubits, odd and psi, a phase shift gate with angle m-pi on qubit, psi, and another controlled Z gate between qubits, odd and psi. This process is repeated in reverse for both Alice's and Bob's sides. The circuit measures the final state of the trigger qubits and stores the results in classical registers. The probabilities of the output states 0000, 0001, 1000, and 1001 are approximately 0.25%, indicating an equal chance of obtaining any of these possibilities when implementing the BQT protocol. These probabilities serve as vital indicators of the effectiveness and efficiency of the BQT protocol and provide valuable insights for its optimization. The phase shift angle is determined by multiplying m by pi. By evaluating the protocol's fidelity at various p and m values, it is possible to determine the specific combinations that result in the highest fidelity. The bidirectional quantum teleportation scheme's results are discussed, focusing on probabilities and fidelity from various simulators. A histogram shows output probabilities from the Air, CASM, and Bellum simulators, highlighting the importance of parameters p and m for high fidelity. Theoretical and experimental results are compared in a table, emphasizing agreement between predicted and observed probabilities. The discussion stresses the effectiveness of the teleportation operation, with simulators generating results closely approximating the ideal scenario of perfect teleportation. The study's findings emphasize the significance of probabilities in coherent state teleportation and the efficacy of the BQT protocol using entangled quantum channels. The paper explores the efficiency of the BQT protocol for quantum teleportation, focusing on the role of fidelity and quantum Fisher information, QFI, in enhancing efficiency. It delves into how controlling the number of partitions and overlapping of multipartite coherent states can achieve pre-shared entanglement. The authors found that a minimal number of probes is required for maximum fidelity, particularly for symmetrical and antisymmetrical states. They also established a relationship between QFI and fidelity, showing that higher fidelity leads to more accurate estimation of Alice's trigger phase parameter. The study compares theoretically predicted probabilities with those obtained from IBM simulators, providing insights into the agreement between theory and practice. The authors emphasize the importance of controlling environmental effects and suggest future work on testing the protocol in noisy channels and exploring other quantum resource kinds beyond entanglement. Quantum information processing encompasses various aspects, including quantum teleportation, entanglement, and quantum estimation. The dynamics of local quantum uncertainty and trace distance discord are key topics discussed. GHZ-like states are also explored for quantum communication. Furthermore, the page delves into quantum estimation, focusing on the quantum Fisher information matrix and its applications. This comprehensive resource serves as a valuable reference for researchers and stakeholders in quantum information science. This page presents a comprehensive list of methodologies, equations, and algorithms used in the research paper to address the complex problem of quantum computing. The authors have employed several cutting-edge techniques to tackle the challenges posed by quantum decoherence and entanglement, which are critical for maintaining quantum coherence and achieving quantum computing's full potential. The paper begins by outlining the importance of understanding quantum decoherence, which refers to the loss of quantum information due to interactions with the environment. To mitigate this issue, the authors propose an innovative method based on quantum error correction codes, specifically focusing on surface codes and Shor's code. These codes are designed to detect and correct errors in quantum information, thereby preserving quantum coherence. In addition to quantum decoherence, the paper also delves into the concept of quantum entanglement, a fundamental aspect of quantum mechanics where two or more particles become interconnected in such a way that the state of one particle instantaneously influences the state of the other, regardless of the distance between them. The authors explore various entanglement generation methods, including Bell state preparation and entanglement swapping, to establish robust quantum communication channels. Moreover, the paper discusses various algorithms that can be implemented using quantum computing, such as Grover's algorithm and Shor's algorithm. These algorithms leverage the power of quantum superposition and interference to solve complex problems more efficiently than classical computers. The authors also provide an in-depth analysis of quantum hardware, including superconducting qubits and ion traps, which are essential components for building practical quantum computers. They discuss the challenges associated with these systems, such as error rates and coherence times, and propose strategies for improving their performance. Finally, the paper concludes by highlighting the significant advancements made in the field of quantum computing and emphasizing the need for continued research to overcome the remaining challenges. The authors emphasize the potential applications of quantum computing, ranging from cryptography and optimization problems to material science and drug discovery, underscoring the importance of this emerging technology for future innovations.